Today I was just going to take, one off to make sure that we're all on the same page as far as graphs and graph algorithms and terminology and all that stuff goes. Hopefully we're all aware of what a graph is, right? For example, let me just go ahead and give you a graph here. Let's see, let's go back over here, we're graphs. So let's go with this one. So when we say graph, when I, at least for, without any other qualification, we mean an undirected graph, right? So this is an undirected graph. And usually we write it as a two-tuple, G equals V comma E, where V is the set of vertices. And sometimes we refer to them as nodes. And then E is the set of edges connecting those nodes. So when we say that, say A and C are connected here, that means that A and C are in the edge set. Right? Well, you could also say that because it's undirected, C and A are also in the edge set. Right? These two things are equal. Right? Only if it were an undirected graph, right? Or if it were a directed graph where you've got this edge and then you've got an orientation where C is going to A or B is going to C, right? Then those two things are not the same thing. If you do have edges back and forth, then you would have to explicitly draw both of those edges, okay? So from that perspective, we are dealing with undirected graphs. We will eventually deal with directed graphs and other types of graphs. But directed graphs have an orientation. Undirected graphs do not have an orientation. And without qualification, we mean that we're talking about undirected graphs. Right? We can also talk about weights or no weights. Right? Each graph could have a numerical weight associated with it, or a cost, or a benefit, or something like that. This is an unweighted graph because we've not drawn any weights here. If we indicate weights, say like 1.5 or 3 or 7 or something like that, then we usually put weights on edges because it costs you to go from, say, I over here to F, right? And there's some costs associated with that. Usually when we say a weighted graph, we mean something like this, where you've got all of the edges going from one node to another node. In this case, it's directed because it has orientation, but it's also weighted because each one of these edges has a weight. But otherwise, again, without qualification, all of the weights are equal to 1. So that's why we're not writing it, right? That's why we don't write 1 times 5, we just write 5. 1 times x, we just write x. Each one of these weights is going to be uniform, and they're all 1. But there's no point in writing that, so we just write it like this. In that case, a path in a graph is a sequence of connected edges, and a cycle in a graph is a path that begins and ends at the same vertex. So clearly there are lots of different cycles here, right? I to F to over here, right? There's a cycle all the way around the perimeter of this graph is a cycle. Now, this is a path. If I go from A to C, go from C to A, and then back again and over to D. That's a path, granted, but it's not a simple path. It's what's called a complex path. We don't mean that, right? Why would you waste your time going back and forth between two vertices here, right? If there is a path from A to C to D, right? There's also another path from A to B to D, which forms a cycle, right? So we're already away from trees, whereas a tree is an acyclic graph, and you have a guarantee that between any two vertices, there is exactly one path, right? With a general graph here, we don't have that structure anymore, right? We've lost structure, basically. And so all of the nice tree algorithms that we've seen before don't necessarily are not necessarily efficient when we go to a full graph like this. Okay. The length of that path or cycle is the number of edges on it. Right? So, for example, if I have a path from A to E, right, the length of that path is 1, 2, 3. How many nodes are on that path? 1, 2, 3, 4. So, just like any path, if you've got 4 nodes, how many things are in between it? If there are n nodes in there, then n minus 1 edges, right? We usually use the designation n and m to indicate the size of the vertex set and the size of the edge set. And therefore, we define a tuple like this. Now, just to make sure that we're all on the same page here from, say, 235, there's very special types of graphs. For example, K sub n is a complete graph on n vertices. So what does a K1 look like? Well, a K1 is just a single vertex. What does a K2 look like? There are two vertices, and all of the edges are present, so you've got one edge, right? So n, 1, and 2. What about the size of the edge set here? Well, 0, 1. Let's see if we can suss out any pattern here. If I've got 3 vertices, it's a triangle. So 3 vertices and 1, 2, 3 edges. Okay. What does a K4 look like? You have 4 vertices. How many edges? 1, 2, 3, 4, 5, and 6. All right. What does a K5 look like? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9. Is that it? 1, 2, 3, 1, 2, 4, and then there, 10, right? So 10 and 5. Dot, dot, dot. If I just go with the general Kn, what is the size of the edge set here? So think about how you form edges. Given two edges, you have to draw an edge between them. Right? If you have, vertices, right? U and V. So if you have n vertices, how many ways are there of choosing 2 of them in order to draw the edge between them? N, choose 2. Right? That's going to be equal to n times n minus 1 all over 2. And there's our answer. Right? Copy. So, paste. There it is. Make it smaller. There we go. N choose 2, which is equal to n times n minus 1 over 2. That is equivalent to this, all of these values right here. Right? Plug in 5 over here. 5 times 5 minus 1, 20 divided by 2 gives me 10. Right? So, in general, you can have that n is at most big O, that the edge set, the size of the edge set, is at most big O of n squared. And if we're using n as the size of the vertex set here, then they're polynomially related, right? You can have at most n squared relationships between n elements. Right? Now you can have special types of graphs that have, say, self-loops, right? Those are pseudographs, I think. Pseudographs. Right? And they are necessary in general because this is a reflexive relationship, right? But we're not going to look at those. You can have multigraphs, where if you've got 2 vertices here, you can have 1, 2, 3, 4 edges between them, right? These are multigraphs. Again, we're not going to look at those kind of graphs. Generally, you have like a morphism between those types of graphs and regular old types of graphs anyway, right? That if you have 2 vertices here, you can take 4 of these edges, you can collapse them down without really changing the structure of the graph. Right? You can do that stuff a lot. For example, you can replace an edge here with an entire path, right? By introducing intermediate nodes here. 1, 2, 3, 4, 5. That way you can take a weighted graph of weight 5 with that edge, and all you have to do is transform it into an unweighted graph that's slightly larger, right? So there are morphisms between all of these types of graphs, and that's why we're just going to stick with the basic type, right? Because Anything that you say about this, you can generally apply it, or you can generally modify it or adapt it to any other type of graph. Right? Okay. So where does that bring us? There are lots of ways to represent graphs. An adjacency matrix, adjacency list, maps, just full-on sets, right? Because that's what they are, et cetera, et cetera. Let's take a look at a small example here. Let's go ahead and go with A, B, C, and D. Right? Generally, we can label edges, or we can label the vertices, but that's just for visualization purposes. Okay, so if I've got a graph that looks something like this, right? It's not a complete graph, right? So it's not a K4, but it's got some edges here. A way of doing this with an adjacency matrix is to establish a 4x4 matrix, or in general an n by n matrix, where you associate each vertex with a row and then again with a column, usually in the same order, right? And what you do, right? What you do is you set zeros and ones. 0 indicates that it's not connected, and 1 indicates that they are connected. Now, along the diagonal, those would be those self loops that we've described, right? Is A connected to A? Well, implicitly, yes, right? Implicitly, so go ahead and make the diagonals ones. But understand that that's not really an edge, right? If you are at A, how do you get to A? Well, you just stay there, right? You don't travel out and then come back, okay? A is also connected to B and C, so those would be 1 and 1. And since it's undirected, it's going to be symmetric. If you were to take the transpose of this and rotate this matrix about the diagonal, it's going to be symmetric. This thing over here is associated, this and this are associated, this and this are associated, and of course the entire diagonal is 1 as well. Let's see, B is connected to A and C, but not D. So these will end up being zeros, 0 here. And then finally D is connected to just C and itself, so 0 and 0. There's the adjacency matrix for this thing. You can also have an adjacency list, where you associate with each vertex a linked list. Right? So A is connected to B and C. Right? B is connected to A and C. C is connected to all three. So you'd have, not necessarily in this order, but B and D. Right? There we go. And D is only connected to C. So it'd end up being a linked list of size 1. Okay? That's an adjacency list representation. Now, since it's undirected, of course, A is connected to B, but also in B's list, A is present. So you'd have to keep track of both of those things. If you're going to go with an adjacency matrix, you'd need to make sure that it is that it's symmetric. If it's not symmetric, then you have, to go back here, then you have a directed graph, right? Where you can go from A to B, but then across the diagonal, you might not necessarily be able to go to B to C, B to A. Right? Right, that's an adjacency list. That's an adjacency matrix. Another one would just simply be a set, right? You could have a, I don't know, here's Python. V is equal to set. Can you do that in Python? Is that right? Yep. All right, and then so V dot, what is it, add or append? Forget it, let's do it. Right. Preview, forget what's up there first, right? V, here's my vertex set. It's going to be a set, and what do I do with it? V dot append, or is it add? Add 0. V dot add 1. V dot add 2, and V dot add 3. Right? So what I'm doing there is actually, let's do it with strings, like we did A, B, C, and D. Print B. All right. What is it? Network x dot pi. Yep, ABC. Okay, add. That makes sense because a set is unordered. I didn't think it would be append. I would be surprised if it were append because append is at the end. A set is unordered. I don't know. Pleasantly, okay, good. I'm pleasantly not surprised, right? That would not make any sense. So there's my vertex set. What would I do with my edge set? E would also be a set, but it's not a set of individual elements. It's a set of tuples, right? So E dot add, if I want, what does my graph look like here, right? A goes to B and A goes to C. So E dot add, A goes to B and A goes to C, right? And the rest of them, right? So to do V rest, dot, 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 right? And I would print out V and E. There we go. And there's my graph, exactly one argument. Okay, fine, I have to do it. Is there add all? Maybe not. I can only do one at a time here for some reason. There we go. And there is the beginning of my graph as a set, two sets, right? It's a tuple. And by the way, you can go ahead and wrap those up in Python too. Here's my graph, V comma E. Somewhat satisfying that you can use this kind of mathematical tupling, right? I wonder what happens when I print G though. Probably won't let me do that. Oh, it does. Neat. Okay. So that's another way. You can also use maps, right? You map for example, you could take the map and map a vertex to a set of vertices, right? So there are lots of different ways, but as I hinted at over here in the Python world, what I'm going to suggest is that you use network X. Now we previewed this previously, but maybe just as a review here, I don't want to do that. Let's go ahead and build this graph here. So first of all, you're going to have to import it, right? And that means that you're going to have to install it, network X. If you've already installed it, great. Otherwise, you'll need to pip install it again. It's installed on CSE. Shouldn't be any problems. Okay. You can create a graph here. By default, it's going to create an undirected graph. Okay. Then you can start adding things to it, right? You can add nodes. Let's go ahead and do that that graph. G.add node. And we'll go ahead and 0, 1, 2, 3. Actually, let's go with A. Let's go with B. Let's go with C. And let's go with D. Now, I don't know what we'll print if we print G here. Yep. Graph with 4 nodes and 0 edges. Right. So let's go ahead and start adding edges. I don't know, G.add edge. And we'll go ahead and add an edge from A. What did my graph look like? A to B and C. So A to B and C. Right. I had, how many were there? A to B, B to C. I don't need to do B to A because I've already done it, but B to C. And finally, C to D. Were there 4 edges? 1, 2, 3, 4. Yep, that's all I need. So, now I've got, oh, oops, add edge is not defined. Yes, it is. Oh, dot. There we go. Dot. Was that it? Okay. Dot. There we go. Now I've got 4 nodes and 4 edges. Right? Now the way that I added them here, they are labeled nodes. Right? So if I were to iterate over that node set for u in g.nodes, print u, I'm going to have A, B, C, D. Okay. In your actual assignment, I think that we just ask you to associate them with 0 through n minus 1. Right? And that's good enough. A would be 0, D would then be 3. Right? But you can also have other labels. Right? For example, you can label individual nodes. Let's see, what would it be? Yeah, g.nodes of, let's access A. That gives me the node A. That gives me the vertex A over here. I can add whatever labels to it, or whatever, they're called attributes in general. I can say that, I don't know, eventually we're going to have colors of vertices. We're going to initially color them white, and then when we visit them, we gray them out because we visited them, and when we're done processing them, we black them out so that they're done and we don't visit them again. Right? So I'll go ahead and go with the color here is equal to green, or here, red, because apples are red. B, C, D, B, C, D, red, blue, cyan, D, dark. Just looking for something that makes sense here, right? There we go, it works. And instead of printing out U, what we could do is, let's see, we'll print out a format here, formatted string, here's U, and has the color, I think it's going to be, what is it? G.nodes of U, and its color. There we go. So from this syntax, you can tell that it's all being internally represented as a map, right? I'm getting the node with key D. Then I am getting the value associated with color. Color maps to dark in this case, right? And so when I do this, I think, oh, I need to close it, sorry. I think I can get them all, oh, nope, color. Oh, probably because I used double quotes, and so I need to use single quotes. There we go. Otherwise, I'm escaping out of the double quotes. So this is how you can mix. This is why it allows you to do single quotes or double quotes, so that you can mix internally. A has the color red, et cetera, et cetera. So you can change those colors, of course. You can have other attributes, not just a color, but say a weight. Right? I think that you can do that with edge, right? G.edges, is it? And we'll get, how do I get the edges? That's a good question. G.edges. A, I don't think that this syntax will work. B, there's the edge. E equals, nope, network X, get edge. Get edge data. Okay, so if I just do double here, probably. Yep, okay, I've got it. So edges, I can't do that because that syntax doesn't make any sense. Oh, what was it, edges or edges? G sub. So G sub like this, and then weight equals 5. I think I could do this. Let's find out. Yes, I can. Right? So all I'm doing there is associating the weight of 5 between A and B. Right? There might be better ways of doing it, and if you read the documentation, I'm sure that you can find better ways of doing it. Come on. All right, I'm going to have to cut and paste it from over here. But there is there's a nice tutorial at the front. If you use this, if you use Network X on your last assignment, or on a previous assignment, then you should be familiar with it a little bit already. One other tool that I want to draw your attention to is a nice visualization tool. So it'll take Network X graphs, and as long as you have an appropriate setup here, it will generate LaTeX code using Tixi that when you compile it, it looks something like this. Right? So if you've got a like a large graph and you want to visualize it because it doesn't make sense, in just in data format, you can try to output an actual figure that you can take a look at. In fact, in your handouts, that's how I generated those graphs, I believe. Right? Okay. So that's basic graph representation, right? Yeah. Any questions so far? No, then let's go ahead and review something that we've seen before. To do this, what I want is not just a regular, not just a graph, but a very special type of graph, a tree. Let's go back over here. Do I have trees? Yeah, let's go ahead and go with, well, this one. There we go. So remember the ordering that we've looked at before, right? There's pre-order traversal. There's in order. And by the way, this is a binary search tree, so in order traversal will produce an in order ordering and post order. Pre-order traversal is going to be a root, left, right order. So let's remember what pre-order looks like by doing a really quick example. We start at the root, and that's the root, so 9. Then we go left, and after we're completely done with the left subtree, then we go to the right subtree. Okay? So I'm at 9 here. Now I'm going to go down to over here to the left subtree, 7. Right? Then I do the left subtree and then the right subtree. So I go down to the left subtree, 4. Right? Then I go down to the left subtree again, 1. And at that point, I do the left subtree, but it's empty, so you don't do anything. I do the right subtree, it's empty, so you don't do anything. And so I start coming back up. Okay? 4. I already did that. So now I go down to the right subtree. Right subtree. 5, and I come back up. For the same reason, because it doesn't have any children. Right? I come back up. I come back up because there is no right subtree to off of 7, so I'm all the way back up at 9 now. Okay, I'm going to go down to the right subtree now. That's 30, or sorry, yeah, the right subtree, and then I go down to the left subtree, 20 and 17, right? And then because there are no children, I start coming back up. I go back over, come back up, 23, come back up. 30, come back down, go back up, 40, oh wait, I already did 30, sorry, 23, and then finally 40, and then we're done. Right? Now, I'm going to go into my highlighter here because what about in order traversal? What do? You still do the same thing. You come in here, but you don't process 9. Instead, you do the left subtree, then you process the root, because this is a left, root, right. Right. So I go in, but I wait to process 9 for later. So I go down to the left subtree. I wait to process this until I've done the left subtree. Go to the left subtree. I wait to process this until I've done the left subtree. I process this because there is no left subtree. I process it, so 1. Right? And then I process the right subtree, but there's nothing there, so I come back up. Right? I then process 4. I go back down, 5, ... I wanted to go through those. In fact, really quick here, post-order traversal, what would you do? Come in here. I process the left subtree first, left, then right, then root. I'm not going to have to change any of my arrows at all. It's exactly the same. I come in here, but I wait to process it. I go down here, go down here, go down here, right? There is no left subtree, there is no right subtree, so I end up processing 1. Then come back up, go back over. What am I doing on all 3 of these? Starting at the root, going down as deep as possible, backtracking, finding another route and going down as deep as possible again, coming back up, right? Going back down, process, process. So what have I done? I've just walked around the perimeter of this tree. Right? All three of these are what's known as depth first search. Right? It's just that they differ in when you process what with respect to a tree. Right? What does that same process look like for a regular graph, like a full, a non-tree graph, a graph with, say, cycles in it? All right. So let's just look ahead here. What if I start at I and I go as deep as possible, deep as possible, deep as possible, right? And then I come back and I see, oh, I. That forms a cycle, right? Should I continue and just do that forever and ever and ever and ever? Right? No, there's no perimeter here, right? There's a perimeter right here with respect to that cycle. There's another perimeter over here with respect to that cycle. Right? There are many perimeters here. I want to make sure that I am only doing things once. Right? I don't want to get caught in a never-ending cycle, just going back and forth, back and forth, back and forth, back and forth. So what I need to do is I need to keep track of breadcrumbs like Goldilocks. Not Goldilocks. Hansel and Gretel. There we go. Hansel and Gretel. They went into the forest, and their father led them in the forest for whatever reason, trying to get rid of them. They were smart enough to take a piece of bread and leave breadcrumbs behind so that they could find their way out of the forest again. Right? Of course, the birds ate it, and they weren't able to find their way out. But we're going to leave breadcrumbs. The breadcrumbs that we're going to leave are highlights. Oops, where's my highlighter? There we go. Let's go with green. Green looks nice. So if I start at I, what I'm going to do is I'm going to color it and say, I've been here before. Right? So that when I come around and see it again from this perspective, oh, nope, I don't want to go there because it's already been visited. Okay? So those are going to be my breadcrumbs. Let's simulate what it would look like. Right? Really quick here, and then we'll get into the details. If I start at I here, and I go as deep as possible into the tree, right? Or not the tree, the graph, right? I have to make decisions at each turn, right? If I start at I could go to F or I could go to A. Which one do we want to go to first? Any votes? Random? We could do a random. What's a more, well, a computer could be programmed to understand random, right? But what's easier to program? So A versus F. Which one would you naturally go to first? A. Why? It's lexicographic order, right? And when you go to program this stuff, I think that we tell you go in lexicographic order or go in, like, if it's weighted, 3 and 1. Go to the vertex whose weight is least next. In which case that would be, okay, well, I would look at 3 and 1. Okay, well, I would go 1 first. This is not a weighted graph, so let's just go ahead and go with lexicographic order, okay? I'm going to go start at, and now here are my breadcrumbs visually. I'm going to start at I. Let's go with this. It's a different color. I'll go to A. Now, I look around my neighborhood of A here. Do I immediately want to go back to I? No, that's where I came from. How do I know I came from there? Well, I see this breadcrumb right here. So among my other choices here of C, B, and H, which one should I go to next? If I'm going lexicographic order, B. Okay? Again, I look at the neighborhood here. I don't want to backtrack to something that I've already been to. Right? So candidates would be C, D, and G. So let's go over to C because it is lexicographically next. Once again, I look at my neighborhood here. Now here's a different story because I did not come from A. I came from B according to my breadcrumb right here. Right? But A is in this path that I took here. Right? If I looked back 2 breadcrumbs, I see that I already came to A. Right? So I don't want to go there because I've already gone there. I don't want to go to B because I just came from there. And so the only choice now is to go to D. From D, I've got an even larger neighborhood here, but C and B have already been visited, so I have a choice of G, E, or F. If I'm going in lexicographic order, I'll go to E next. Okay? From there, I will really only have one choice, so to go over to F. Right? And at that point, I'm at a dead end. Right? I could go to I, right? I'm not really at a dead end. But if I go to I here, there's my infinite loop. Just keep going around and around and around forever. Right? So at that point, what I do is I start backtracking. Let me give myself another color here. Right? There we go. I backtrack over to where I came from. Were there any other options coming out of E? No. Well, I just tried that direction down the maze. I came from that direction, so no more choices. Backtrack again. At D, I see that I've already been to C. I came from C, right? Actually, technically, I came from E in my traversal, but to get there to begin with, I came from E. So that's not a choice. That's not a choice. That's not a choice because I've already visited all of them. Also, B is not a choice because that was in my original path to get here. But I do have another choice to go to G. Within G, I'm looking at all the, I've visited this, so those aren't options. But I do have an option over here to go to H. Right? And now fast forwarding, since I've visited everything at this point, what do? Backtrack, 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 backtrack. And all along the way, I would be checking, is there anything more to visit? Is there anything more to visit? And I would be answering no, 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 no all the way. Okay. All right. So let's codify this as an algorithm. Well, actually, let's do that again, but let's keep track of some additional information here. Right? What I'm going to want to keep track of is, I want to keep track of state. What I mean by that is it unvisited? And we color these white. Right? Is it been visited? And these will be colored gray. Except that my highlighter color is what? Green. There we go. Green. So green, gray, whatever. Right? And processed. In which case, what's my other highlighter color? Gray. There we go. Or black is what we usually call it. Right? Okay, just spammers. Sorry about that. Anyway, I'm going to keep track of the state. I'm going to keep track of when it was first visited and when it was processed. In other words, I'm going to keep track of when it becomes unvisited, you suddenly visit it. When you color it gray, or in this case green, right, then that means that you have visited it first. When you go from visited to processed, because there are no other nodes to process, you're at a dead end and you need to start backtracking. That's the second time that we look at it. Okay. So once again, let's start at I. To do these two things, I'm just going to simply keep track of a counter. Right? 1. Right. That's going to be its visited time, and I'll delimit that with a colon, and then the second number that I write down, that will be its processing time. Okay? I start at I, and it's been visited. So my highlighter color here, I'll color it in green. There we go. I visited it. There. Okay. Exact same process as before. I go over to A, and I discover it at timestamp 2, and I color it green as well. All right. Keep going. Where did I go next? B. Right. And it's discovered at 3, and it is now colored as well. Green. Right. Continue. I went to C, discovered it at timestamp 4, and colored it green. Okay. Keep going. D, 5. Right. From D, I went to E, 6. And I'm coloring along the way here. Right. From there, I went to F, discovered it at 7. And here's where something different and interesting starts to happen. Okay. At this point, I look at the neighborhood. How do I know that there's no option here? I look at all of its neighbors and I see that they're all green or gray. Right? So meaning that I know that I shouldn't go to them. That's how I'm keeping track of my breadcrumbs. These labels, this is why I showed you how to do a label, right? You can label it as red, blue, cyan, dark, right? How do you keep track of where you've been? Well, it's going to be green, gray, whatever. I would actually, instead of colors are used for visualization purposes. In your actual programming, I would actually use the words that mean what it is. Unvisited, visited, processed, right? Okay. But otherwise, we're done with this. So we start to backtrack. And I process this at timestamp 8. And since I'm done with it, I'm changing colors here, and now it's gray. Or it's black. It's been visited. We're done with it. Okay. I backtrack over to E, which has 7. Right? Or sorry, no. You can keep separate counters, but I'm keeping just one counter here. Right? And you see that it's incrementing 1, 2, 3, 4, 5, 6, 7, and it doesn't matter. We're just using one counter, so increment 8, 9 for each step along the way. Come back. Now that's colored gray or black, I guess, because we're done with it. There we go. We come back up to D, color it black, and oh, actually no, sorry, no, we don't. What do we do now? We still have an option to go over to G at timestamp 10. It's discovered. That gets colored green because it's the first time we've seen it. And then we have another option here to go to H. There's 11. Right? And that's colored green as well. And at this point, everything has been visited. We only process it on the, finish it on the way back here. Right? So 11, 12, 13, you can imagine what it's going to look like. Right? Color that black, color that black. Right? We come back to D, and that's going to be processed at 14, 15, 16, 17, and 18. And all along the way, I would have been coloring these black, 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 and black. Right? Maybe a darker shade there or something. Right? So those are what are called artifacts. And using those artifacts, you can generate a lot of things. For example, you can generate the DFS tree. Right. So the primary route that I took to do all of this, guess what? What kind of graph is it? Does it have just the red here? Does it have a cycle? Nope. That's why we call it a tree. I, A, B, C. I, A, B, C. This is the route that we took. Then after C was what? D, E, F. D, E, F. There we go. But then remember, we started backtracking. We backtracked. Once we got to D here, we went over to G, H. G, H. There's the DFS tree, right, that you can generate from this. Now, what about all of these other edges? For example, what about I to F, right? Oops. What about I to F? And what about A to H? I to F, and A to H. Those would not be in the DFS tree, but those edges tell us something. What do they tell us? Here's the primary path from I to F, and you have another edge here connecting it back. What does that form? A cycle, right? So DFS, first application, cycle detection, right? If you ever encounter a visited or a processed vertex along the way, along your that you didn't immediately come from, right? That I went, oops, come on, there we go. I went here, 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 and then, oh, I see a green vertex over here in my neighborhood that I did not immediately come from. I have a cycle. Report that cycle, right? Not a tree, right? So given a graph G, is it a tree or not? Well, does it have a cycle or not? It has a cycle, therefore it's not a tree. There is no cycle, therefore it is a tree, right? That would be a tree, right? And these are what are called cross, forward, or back edges. Now, in general, you can. It depends on the type of graph that you have, a directed or undirected graph, but you can classify each one of these edges as either a forward edge or a back edge, right, or a cross edge. Now, for undirected graphs, these are the same. Why? Because it doesn't matter if you go forward, or it doesn't matter if you go backwards. It's the same thing. A cross edge would look something like this. F to H, if we had any cross edges. Now, is F and H, F and H are not connected here, right? This is not an actual edge. So for the weekend and the break, I'll give you a question. Can cross edges exist in a DFS tree? In other words, could this edge be here? To be there, it would have to be here. How would that have changed our DFS? I'll let you think about that, and then we'll review it when we come back on Wednesday. You have your assignment 6 due tonight. It's all written. Make sure that it's in Canvas on time. Make sure that it's readable in a PDF form. There are already a couple of questions on there about it, but otherwise, no programming. I think this is the one that's going to take me a while, but it's a night game, so don't expect any grades until Saturday evening. Okay? All right, then have a good break.